Okay. All right. This is about where we left off last time, right? With in queue. But we had that funny edge case of what happens if the queue's empty, right? So when you look at this code here, okay, there's in queue. It's not as simple as like, okay, the general case is I have front, which is a node, which is a node. Let's say it's rear, and this is rear, right? The general case is simple. Rear is the new node. Like, let's say this is the new node here. Okay? The one containing the element I'm in queuing. What I do is I say rear's next is the new node, and then rear is the new node. There. Done. Right? There. That's this general case. And the general case is relatively simple. But when we look at this code, there's a little bit more going on here. But let's take our time. First and foremost, what I will say is, I think I said this last time. This is coded in kind of like, arguably like an elegant way. And in doing so, it might make it feel a little bit more complicated than it needs to be. I could probably have coded this in a little more explicit, clearer way. But there's some niceness to the way this is coded. So what do? I start with a new node containing the element. Great. Now, let's say we have the case where we happen to have an empty queue where rear and front are both referencing null. By the way, when I say it references null, you don't have to think of it like this. They just both reference nothing. I'm representing null as just this dot. Okay? So I say if it's empty, okay, front is, I create a new node, n. If it's empty, front equals the thing I'm in queuing. 2 in queue is the n in this example. So I say front, you reference that. Otherwise, I say rear dot set next to the in queue, which is what we just did actually. But we'll revisit this in a moment. And either way, if it was empty or not, either way, I say rear equals the thing we just in-queued. Oh, I can get rid of that. Like that. There. Right? So either way, the new thing I added should be the new rear. Increase size, return true. So that was the empty case. But let's go to a case where we have front is some node. There, it's a short one, whatever. 2 elements in it. All that really matters is that it's not empty. In fact, let's even make it more like this. There, we've got a new node here, n. And I say, okay, is it empty? No, it's not empty. So what do? I say rear, set your next to the new node. And then either way, rear is the thing we just added. Done. Do we see? And we can do it again. Make another new node over here, n. All right, is it empty? No. Okay, rear, your next is the new node, and then rear equals the new node. There we go. So the idea here is, no matter what, rear needs to be updated to the thing that we just added. The thing that we just added to the back is the back, right? The thing that we added to the rear is now the new rear, either way. The only other case is if it's empty, the front needs to be set to what's being in-queued, and the rear needs to be set to what's in-queued. If it's not empty, front stays the same. But rear's next needs to be updated. And there. That's it. It's by no means overly complex, but I don't know, there's some like elegance to this, I think. Any questions about this idea? Yeah? No? Happy? Okay. So in-queuing into an empty queue, this is what we would call an edge case. We've already explained it. Great. In-queuing to a non-empty queue, we just explained it. Great. Now dequeue and first. All right. we got to be careful with DQ. And we're going to talk about the examples why, the cases. So first and foremost, I think it's easy to go to that edge case of, well, what if the queue is empty? What do? Throw a new exception. Same idea we did with the stack, right? Now you might remember that with our implementation, like when we talked about Java's queue interface, they actually had two versions of like in-queue. One where, or sorry, they had two versions of DQ and first, whatever they call them, I can't remember. Like offer and, I don't know, whatever they called it. If you try to DQ an empty from an empty queue, the Java one, it might throw an exception depending on what method you use. It might throw an exception, otherwise it might throw a sentinel value, a special value, null. And you might say, well, why would I want one over the other? If you did, it gives you the flexibility, that's all. All right, so if it's empty, throw a new exception. Otherwise, we get the return element from the front, because the front, if it's not empty, front exists, right? So let's go to a general case. Let's say, whatever, it's not empty. It's not a queue of size 1, which is another edge case we'll see in a moment. What do? Well, to DQ, we need the data from the front. So we get the data from the front. And then I say front, UB fronts next, right? That's just removing from the front of a link structure. It's the same idea with the stack. Top equals top dot get next, right? So we just update it to be that. Right? Great. This has nothing referencing it anymore. It's as good as gone. Okay? But I have a very special, funny little case. Because imagine this is our situation. Okay? And I say, okay, DQ, great. Like ignore this logic here for a second. Okay? What happens if I DQ from this? Okay, get the element out of here. Front equals front dot get next. Well, that makes sense because front should be null now because it's empty. But rear never gets updated. So in the off chance, most of the time, the general case is when you DQ, rear gets left alone. When you remove the thing from the front, the rear is left alone. Unless the front and the rear are the same thing. Unless the result of the DQ means it should be empty. In that case, we've got this like dangling thing that never got updated. And you might be like, oh, okay, in queue. Oh, go to the rear, set the next. But the queue should be empty. Everything gets all messed up. Yeah?
I'll let you get to that.
All right, so the logic here is, okay, we get the data, update the front, decrease the size. Is it empty? If it is, well, then we resolve that by saying, okay, no, reference is null, nothing references this, it's as good as gone. That solves the problem. Yeah?
So it's still considered empty when rear still references that other.
Because the size is how many things in the queue do I care about? Right? So is empty if we scroll down. I guess I don't even include them because they're just like return size. Or return size equals 0. Not equals 0? Equals 0. It's empty, yeah. Cool. So here's DQ and here's first. First, it's straightforward. Just return the data from the first. Nothing gets removed. We're good. It's good. We're good to go. All right, any questions about what we're seeing here? This is our linked queue. There is more logic to it. There's more we have to be aware of in like those edge cases. And it's funny because like, well, in queuing into an empty queue is an edge case. But dequeuing from an empty queue is an edge case. But also dequeuing from a queue that has one element in it is also an edge case. So we have to be aware we're considering what happens in these special circumstances. All right. Although not true in general with the provided implementation link queue, missing this edge case in the DQ would not act. Yes, so here's a fun observation. You might say, well, look, if we have this case where front referenced null, but rear referenced this, but the queue still knows it's empty, okay? But rear's still holding on to this thing, and it really shouldn't be. If you look at the implementation of in-queue, like look, if you do a DQ now, it's empty because the size is 0. Rear's still there, but size is 0. So the DQ would throw the exception. It's fine. But when you look at the in-queue, what would happen? We immediately say, is it empty? If it is empty, so let's say we're doing an in-queue. If it's empty, front equals that. Rear now equals this. And that thing that was kind of like left now is resolved and it disappears. It's fine. It's gone. Right? So you might say, that edge case, actually, we can get away with ignoring it because it eventually will resolve itself. And although that's true, I think we all kind of have an appreciation why. Clean your code. Like, come on, what are we doing here, right? Like, just because that's true doesn't give us an excuse for having weird crap existing that really shouldn't be there, right? If it shouldn't be there, it shouldn't be there. If it's empty, rear should be null. So even though, it did yeah, but it shouldn't be there. Get rid of it. Make your code as intentional as possible. I saw someone had a hand. Yeah.
So, and then 2 in queue would automatically reference null. Its next would be.
I'm sorry, I'm not clear on the question.
It's like how that works. Its next would be null automatically.
Yeah, every new node that we create, its next is always starting at null. So every node that we create, yeah, it's always null. Yeah. So note, yeah. So a missing edge case would be a problem. Okay, whatever. What's the computational complexity of the DQ? It's not a trick question. It should be, you all should be able to be like, obviously it's, what is it? Obviously it's what? 3. But use that big O terminology. Constant. It's constant, right? How many, like the amount of time this takes does not depend on how big the queue is. Same thing with the in queue. It's constant time, right? It doesn't matter how big it is. So queue variations. Well, there's a lot of queue variations out there. A queue is just this first come, first serve idea, right? And we see these everywhere in real life and in computer systems. And there's a lot of variations that you could come up with, but here's a popular one, a priority queue. A priority queue is a pretty big variation of a queue in terms of like what it's doing. But with a priority queue, which by the way is what you need for assignment 3, a priority queue it's a queue where it's first come, first serve, but things that have a more important priority, things that are deemed more important, come first. It's like triage at a hospital, right? Although you were there first, the person coming in with their arm falling off might get helped before you, who needs the stitches on their hand, right? So first come, first serve, but they're going to prioritize things as they're coming in. So the what? Everything would be the same, except, now I have to be careful. The idea here is I in-queue things with its data, and every data is accompanied with some priority. Okay? So if we think, I've got people that want to go to the hospital. Right? They all show up, but maybe they come in with different priorities. And here maybe a high number is more important or something. So if you have a higher number, you need to be served first. So the idea is, even though this person may have maybe the order that people showed up was like 1, 2, 3, 4, even though this person showed up third, they would be served first because they have a higher priority. So the idea is, and I know I'm saying DQ here, but try not to think so much about the DQ method as like the how, but think about the what. I in-queue people with a priority, and when I DQ, I get the data that the next thing to come out should be the thing with the next most important priority. So I should come 7, 5, 3, 2. That's the order they should come out. Okay? So everything would need to be the same except DQ. In terms of what DQ is, like the what, right? The things coming out aren't based on the order they were added. It was based on their priority. And then secondary maybe is based on the order people are added. So like if 2 people show up with a 7, well, okay, that could be first come, first serve. Yeah?
Could you do like something similar, but you keep DQ constant and NQ is?
Well, that's the question, is how? How do we implement this? So if the idea is DQ, get the next most important thing. And I'm using important here because I don't want to say like the biggest priority, because priority might be a big number or a low number. Things with a higher, a more important priority might be things with a lower number. It all depends on what we want, right? So when it comes to the how, well, I think this is exactly what you're getting at. How do we do it, right? All that matters is that I go, when I DQ, I want this one, and then this one, and then this one, and then this one. That's what I want. How do I do it? Well, what I could do is when I do an in-queue, which was constant time, right? But what I could do is when I in-queue people into that priority queue, I could find where they belong, such that if these people are being added to the queue, I would have the 7 followed by the 5, followed by the 3, followed by the 2. But that requires, like, let's say I want to add someone with a 4. It's not as simple as like, oh, go to the end and add, which was constant time. I have to go, do they go here? No. Do they go here? No. Do they go here? Yes. I have to search for where they go. And what's the time it takes to do a search? If I have n things, I got to look at n things. That means the in-queue for this situation is linear. But then a DQ is the same. Just take the thing from the front. So the DQ is constant still, but the in-queue becomes linear. However, what I could do is do the opposite, where in-queues, just keep in-queues constant. Always add things to the end. But DQs, I search. So if the order they were added was 3, 7, 2, 5, I go through and be like, is this the biggest? Is this the biggest? Is this the biggest? Is this the biggest? That was the biggest. I do a search for the biggest on the DQ. So in this situation, in-queue is constant, but DQ is linear. This is a perfect example of what I was talking about last time or maybe the time before. There's no free lunch. You win some, you lose some. You could win over here, but then you're going to lose over there, and vice versa. Sometimes there is a free lunch. There's no free lunch here. You can have a great DQ, a bad in-queue. A great in-queue, a bad DQ. What do you want? And that's up to you to decide. What would you pick? If you picked, like if you were having to implement this, which implementation would you pick and why? Don't answer it right now. I want to give you 30 seconds. Think about it. Why would you pick the one you're picking? I have an answer in my head. Just we'll give everyone a chance to think. To me, there's like I have an answer, and I think I have a well thought out reason for my answer, but I'm not really right technically. But like to me, I have a clear answer and I have method to my madness. But what do we think? Who's got an idea? What were you going to say?
I would take the NQ being constant because you do it way more often, depending on the problem, you will do it more often than DQ.
That's a good point. So at most, you could have the same number of DQs as InQs, right? Because you can't DQ more than you InQ, but it's possible to InQ more than you DQ, right? Maybe you solve your problem and the list is huge still, or your queue is huge still. Does that make sense? You can never have more DQs than InQs, right? So because there could, in theory, be more InQs, make the InQ constant. Makes sense, yeah? That's a very good answer. Does anyone have any other idea? What were you going to say?
I'd probably go the other way around, because if you were to print out the queue, or like two-string queue, if everything came out like it's an unordered
Yeah.
array, that could cause confusion there.
That's a really good point, is having the data, it's almost like there's value in having the data ordered. That's a good point. And like a perfect example is like, well, think of how easy this two-string representation is. And you might say like, oh, should we really be making these decisions based on ease of implementations of things? Yes, you absolutely should be, especially when it also has a natural ordering to it. That's a very good point. What were you going to say?
I had a similar idea here. Then your front would also be the highest priority, like a line or like something like a hospital.
Yeah.
And it might have more like edge cases in the way that like it's not just a linear search finding the biggest and setting it. It'd be like you'd be going through and it's kind of like the other NQ or DQ you've had where it's like if it's empty, if it's like stuff like that.
Interesting, yeah. So a little, again, you're thinking ease of implementation, and that's a good idea. Here's another thing to consider too. By the way, both those points, phenomenal points. Very, very good points. Here's another thing to think about though, and maybe somebody thought of this, maybe not. Now at the end of the day, the computational complexity is the same. But if we're trying to be aware of, okay, the total amount of work being done here, consider this. When I'm in queuing and things are ordered, like, well, let's do it like 1, 4, 4, 5, 7, 8, 11, 15. No. Right? And this is what I have. If they're ordered, and now I'm going to draw, let's say, okay, start yelling out these numbers in an arbitrary order.
5, 4, 7, 4, 1, 11, 8, 11.
There's only 111, but 15?
Oh, 15.
1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Well, we did pretty good. Yeah. So, if I have to scan for the largest number here, which happens to be at the end, which is just convenient, how many things must I look at in this list to know, to know that I found it? All of them. I have to look at all of them, all n, right? Where here, best and worst case scenario. If this was 55, I still have to look at everything to see if I didn't find a 55. Where here, if I want to insert like a 6, I only need to go, and as soon as I find where the 6 goes, I know exactly where it goes. I don't have to keep going. Now, in the worst case scenario, I do, because it's possible I'm trying to in-queue a 55. And then I go, does it go here, 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 here? Like, but there is like some stopping early here, right? So you might say, well, on average, if you were to do this 1 billion times, on average, where is the insert position going to be?
The middle.
The middle. For every time it's the end, it's the beginning. For every time it's the second last, it's the first, right? It's on average, the insert position is going to be in the middle. meaning that on average, it's going to be like 1/2 of n, which it's just a coefficient. We don't care. It still scales as n. But we still can use the fact that it's 1/2 of n. If you were to run this a billion times and time each of them, this one might be faster, you know? That's kind of the point. So at the end of the day, there's no correct answer for what's right. And it might really depend on what we know about the problem. This is another common thing in computer science and programming when solving problems is the more we can come up with a general solution to a problem, but the more we know about the problem and the more we know about the data and the more we can exploit about that information, the more we might be able to squeeze out of our algorithms. If we know something, we can kind of go like, well, but actually we can do this to make it a little better. In general, we can talk about pros and cons, but for your particular need, like on the assignment, as time goes on, you're going to be adding more and more things with smaller and smaller, smaller is better in this case, like more things at the front of the list. Than at the, I don't know. And that's information that you might think about. It doesn't, you know. Any questions about that idea? And here's a queue, just playing around with a queue. Why does this work? Well, we've got a queue, but it's a linked queue. Hey, cool. All right, now array queue. All right, I know we kind of spoiled this in lab yesterday, but it is what it is. We need to make an array queue. We don't need to, but we're going to, right? We made an array stack, we made a link stack. We make it a link queue, let's make an array queue. But it turns out making an array queue is kind of tricky. Or it's not that it's tricky, it's that in order to have a good one, we got to get clever. So in order to make a queue, we need a container, a way to keep track of the front, the rear, the size, whatever. Now we want to make an array queue, so let's make the container an array. So here's idea number one. This is what you did in lab yesterday, or what if you're going to do in lab today. So what we're going to do, we're going to use an array, and we're going to keep track of the front by virtue of making it such that the front is always an index 0. Okay? The front of the queue is always at index 0. Simple, right? Is this workable? Yeah, entirely. And what we'll do is we'll keep track of the rear in the same way that we keep track of the top in a stack. It's always like the next available spot in the queue. Now we got to be careful though, because every time we dequeue, we got to move some things around, but it's entirely workable. So let's think about what this would mean. The size also similar to a stack. If we have the rear is always the here I'm saying keep track of the rear index. Really, it's like the next available spot, but yeah. It also does double duty as the size. So here's the idea. If I in-queue something, you put it in rear plus plus. If you remove something, we got a bit of a problem such that okay, imagine we got rid of this one here. We've got this empty spot at index 0. So like here. A, B, C, D, let's just whatever. They're empty, they don't matter, right? If I dequeue A, the front's always supposed to be index 0, so what do we have to do? Move B down, move C down, move D down, there. But we know we've solved the problem. Oh, if rear was here before, 0, 1, 2, 3, 4, we'd also have to decrease rear, right? We have to keep track of that. But that's what we got to do. Clear? Perfect. Yeah, okay. So first question is, will this work? Yeah, it'll be a queue. Knowing that this is an array implementation, will something like an expand capacity be required? Yeah, we might run out of room in our array, so we might need an expand capacity, which is a linear time operation, but we amortize it. So the in queues, although it's you know, it's possible to be linear. We amortize it. We say the inqs are constant time. But what's the computational complexity of a dq? Well, getting the element is easy, but filling that gap is a problem. If I get rid of b, the front, based on what we just said, the front has to be at index 0. I have to fill it. And the way I fill it is by shuffling everything down one. If I have 2 things, how many do I have to move? If I have 10, how many do I got to move? If I have n, how many do I got to move? It grows linearly. Long story short, every dq is linear. Now, in the scope and the big picture of the list of computational complexities, linear, not so bad, right? Linear, we're pretty happy with linear. But look, we just saw a linked implementation that had a constant time dq. And if you're given the choice between a constant time and a linear, you take the constant time. Linear is not bad, but it's a hell of a lot worse than constant. So, all right, this is perhaps a bit of a problem here. To be clear, it works. It is a queue. In order to be a queue, it needs to do the what of a queue. The how, it'll work. Kind of annoyingly so, but it will work. So it's still a queue. But knowing that we have this issue of moving things down, maybe we can modify our implementation idea a little bit. We're still going to use an array container, but instead of always saying that index 0 is the front, let's just make another field. Making another field is cheap. Making another variable that your class keeps track of, it's nothing, right? So we'll make another field called front, and we'll keep track of the rear. And then size will just be front, rear minus front, right? But like what I mean is, what I could do in this situation is, let's say I've got, okay, A, B, C, D. So 0, 0, 1, 2, 3, 4, right? What's 4 minus 0? 4. There's 4 things in here. If I dq this, what I can do is update it to be like that. And now, well, 4 minus 1, that's 3. There's 3 things. So we can keep track of the size by just taking the difference, right? And yeah, and now we live with this, you know, okay, it's not at index 0 anymore. That's not that big of a deal, I guess. We'll just keep track of the fact that whenever we dq, we just have to remember where the front currently is, right? So something like this, right? There we go. Yeah? Yeah, there we go. So will this work? Yeah, that'll work. And we've definitely resolved a heck of a lot of the problem of that dq. So look, we got to do an expand capacity. We're going to run out of room, and it's an array. The computational complexity of the inq is amortized constant. The computational complexity of dq is constant time. But I can't help feel like it's kind of, I don't know, it's sad, right? We've got this wasted space. And you might say, here's an entirely reasonable thing to do, right? Okay, D, E, F, I need to expand capacity. Well, then whenever I do an expand capacity, maybe I just kind of reset everything back down, right? So not that big of a deal. We just move everything back down on an expand. Every time we have to do expand capacity, it's linear anyways, so we got to do a linear time operation. Just throw another constant time thing in there to do it the linear, so it's it doesn't matter anymore, right? No big deal. But you got to think, right? We're going to have, okay. Relative to the first idea, we're going to have to call expand capacity more often. What I mean is, expand capacity must be called after n plus 1 inqs, where n is like the capacity, no matter what. Okay? Despite the number of elements actually in the array. Where the first implementation, I could inq n things, deq n things. I know they're not constant time operations, but let's say they are. Or let's just say we're doing them anyways. And my queue is empty, and I still have a lot of array left. Like I don't need to call expand capacity. So here, before, then when I call expand capacity depends on the number of inqs and deqs I have done. Because every deq undoes an inq in terms of like the space I've used. Where this, because of that wasted space, it only ever depends on the inqs, no matter what. So look, at the end of the day, for this implementation, yeah, you know, we're wasting, we're wasting space. And yeah, this is an amortized thing. Just make the queue sufficiently large. Who cares? Fine. You're not wrong. But I don't know. Something about this doesn't feel right to me. You know? Maybe we can kind of fix this a little bit. And this is what idea 3 is. And yes, we did talk about this a little bit in lecture or in lab yesterday. Because a bunch of you couldn't keep yourselves under control and stop yourself from reading ahead. So, here's what we're going to do. We're going to pretend the array is a circle. That's it. Now you're saying, oh, what? Yeah. Here's what we're going to pretend. Pretend it looks like this. Okay? That's just, yeah. Where, I kind of don't like this example at this stage. Here's an example of a queue where, so look, this is the beginning, this index 0. This is an array of size, capacity 100, 0 through indices 99. All right? This is the start of the array, but I don't care about where the start of the array is. I care about the start of the queue. And the start of the queue is at index 98. 98. And the rear is at index 2, the next available spot right there. Okay? So this is going to be our solution. You inq, whatever they go here. And then you increase rear. You deq, you remove, and you update front. But obviously we're going to have to do something special here because what comes after 99? 0, obviously. I mean, we all know it's 100, but with this design, we want 99 to loop back to 0. So this is our idea, at least. So this is how we would think of that exact same example if it was not circular, it was just linear. But if we pretend it's a circle, it's fine, right? First thing, next thing, the thing after, the thing after. Next available spot is index 2. Yeah?
So with that, we would have to have a field that is size?
A field, yes, we would. Although, I mean, you could probably do some weird math. It's probably just easier to have another field size to keep track of, like, okay, it's easy to keep that updated, right? We can't feel proud of ourselves about our fancy math to calculate size based on the front of the rear, but whatever, right? Yeah. Don't worry, we'll feel proud of ourselves in a moment, though, with the fancy math that I know we talked about yesterday. So, pretending this array is a circle, there's no beginning and there's no end. It goes on forever, right? So the order is whatever, 0, 1, 2, 3, whatever, n minus 2, n minus 1, 0, 1, 2, 3, and it just repeats forever. Before and after. It goes on forever. The index that comes after n minus 1 is 0. The index that comes before 0 is n minus 1. Simple as that. If we were to start this circular array, and I were to inq 1, 2, 3, 4, 5, 6, 7 things, this is what it would look like. Okay, with a capacity of 13 array. Then I deq 5 times, I guess. Yeah. This is what it would look like. And then I NQ a couple more times. It would look like that. Okay? So it was 7 NQs, 5 DQs, followed by 1, 2, 3, 4, 5, 6, 7, 8 more. 10, not 10. 1, 2, 3, 4, 5, 6, 7, 8 more. So it was 7, 5 DQs, and then 8 more NQs. And this is where we are, right? So you're at this stage, you're thinking, okay, all right, so we'll just add some logic. It requires adding logic, but it's not too bad. Okay? Okay, 12, okay, it's 11, increment 1, 12, increment 1. That should go to 13, but we'll just have to say, okay, if it goes past the length, restart it at 0. Fine, not too bad a logic. But we can actually use some very simple mathematics to do this without an if statement. You remember this. Mod. It's like, it's basically do the division, but what's the remainder? I don't care about the actual result of, what do you call that? The quotient?
Yeah.
You don't care about the quotient, you care about the remainder. And remember, we're doing integer division here. Decimal numbers are for fools. We want real nice integers, okay? So, we used this before in 161 a lot to check if things were even or odd. If you divide something by 2 and it has no remainder, it's evenly divisible by 2, it's even, right? If you divide something by 2 and there is a remainder, it's not evenly divisible by 2, it's odd. But it's got far more uses than that. But here we go. 4 divided by 2 is 2, remainder 0, 4 mod 2 is 0. 5 mod 4. How many times can you get the number 4 out of the number 5? Once. What are you left over with? 1. 7 mod 8. How many times can you get 8 out of the number 7? 0. Remainder 7. Notice that whenever this number is bigger than this number, you always get back this number. Knowing this, we can use this magic. Right? So, okay, imagine for a second we had a capacity 8 array. Okay? I might have an example of this right here, actually, so I don't want to. Well, let's talk through this. Okay. Assume an array with capacity 10. Let's assume rear is now 9. Okay? 9 should always be the index of the next available spot in the array. So an InQ is called, the new element is added to index 9. Fine. And the rear is updated. Rear should now become 9 plus 1, 10. But there's no index 10 in a length 10 array. Right? So instead, we need rear to go back to 0. This could be achieved with an if statement. If rear is equal to the q.length, rear equals 0, fine, whatever. But notice that rear equals q.length and rear mod q.length is 0. Basically, if I were to increment 9, what does it become? Say 10. 10. Great. Now, what is 10 mod the q length? Q length is 10. So what is 10 mod 10? First answer the question, what's 10 divided by 10? 1. What are you left with? 0. So that's the trick. We say, we take the rear, the new rear, the incremented rear, and mod it with the length. Also notice that when rear is another number like 4, rear mod q length would still be 4, right? So it doesn't change. This mod thing only really does anything when it gets to like, when the rear becomes equal to the length, and then it restarts, right? What I mean is, okay, let's say rear is 4. What's 4 plus 1?
5.
What's 5 divided by 10? 0. Remainder?
5.
So rear is 5. Perfect, right? What comes after 4? 5. Now let's say rear is 9, right? Thinking circular arrays. What's 9 plus 1?
10.
What's 10 divided by 10?
1.
Remainder?
0.
This calculates to 0, rear becomes 0. Oh, perfect. It's exactly what we want. You have a question?
I just don't understand how it works you have something non-zero.
Oh, you mean like, what if index 0 is full?
Yeah.
Ah, then we better expand capacity. Yeah.
How do you expand capacity when it's a circle?
Hold on to your horses.
Oh, God.
We're about to find out. Turns out it's actually fairly straightforward, but you're asking the right questions. It's perfect questions, right? Well, what happens if we run out of room? We still have to expand capacity. How do we do that? It's really not that bad. Yeah.
You just see if rear and front are the same thing.
Well, let's find out. Let's find out. So first of all, okay, does this strategy for updating front need to also be changed or changed? Will this circular? Oh, yes. So updating the rear, we need to use this rear equals rear plus 1 mod the length of the array. We got to do the same thing for the front, right? Because the front could end up in that situation like in this, right? If I DQ'd twice, front would now need to go loop back to 0 as well. So this does require some math for the rear and the front. All right, will the circular array ever run out of room? Yes. Now, okay. So, by the way, sometimes this is not so much a comment about what we're learning right now, but this is more of a big picture idea for computer science. Good enough is good enough. Okay? With an array queue implementation scenario like idea 3, it's quite clear that the superior option, like it's the superior option, and it's not overly difficult to implement. All right? So this example is like it's idea 3 is better, and it's not too bad to implement. But there's going to be a lot of cases and a lot of problems out there where it could become a lot more difficult to have a better implementation. Okay? But if that implementation takes you a week and a half to make, and it runs 0.1% faster, was it worth it? Okay? Now, if you're a good computer scientist, your answer is always going to be like, yeah, of course it is. We got to maximize this, right? We got to, right? You're going to be doing that. But a really good computer scientist knows when to like rein that in a little bit. Okay? So better algorithms always exist. There's always going to be a better algorithm, no matter what. But a subpar implementation may be sufficient, especially when the problem space is sufficiently small. Computational complexity is a very important idea, but sometimes in practice, we lose sight of the forest through the trees. We start to like focus so much on some of these optimizations where it doesn't really matter. And trying to save a few flops. Does anyone know what flop means? Floating point operation, right? It's saving that, it's great and all, but sometimes it's not worth it. And there's a very famous saying by a very famous computer scientist, Donald Knuth: programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs. And these attempts at efficiency actually have a strong negative impact when debugging and maintenance. And that's another point too. If your solution is really complicated and you give it to somebody else and they're looking at it and they're going like, what the fuck, right? Not great. We should forget about small efficiencies like 97% of the time. That's a very precise number, I'm sure. Premature optimization is the root of all evil. Yet we should not pass up the opportunity at that critical 3%. It's like you could say this with like anything, right? And it kind of gets to like 80-20 rule, where like we could dedicate so many resources to optimizing. Like if I have $1 million to spend, right? And everyone agrees that like if we do this, we'll save like 10 babies for every dollar spent or something, right? So obviously we should do that, right? But we could also do this and save 100 babies for every dollar spent. But we end up spending so much time and energy on some of these types of things where we just, weird, bad example, but maybe, whatever, right? Save the babies. I don't know. All right, so how do we do expand capacity? It gets kind of hairy, right? In this situation, whatever, we don't need to expand capacity. We enqueue something, we look something like this. Now, don't get confused. The front is index 2, but the rear is index 2? Yeah. Was it you? Who said it? Someone said when the front and the rear are the same, you might have some trouble. Yes. When the front and rear is the same, when the next available spot happens to be, my goodness, I was having so much fun. All right, we'll pick up here the other, let me finish the thought. When the front and the rear, when the next available spot happens to be the thing at the front, we got a problem. So on that cliffhanger, there we go.